Hi everyone, today we're covering topic 2.5, Lewis diagrams. So this should be a review from a previous chemistry class, but originally this was developed as a method to denote the potential bonding electrons by using a dot to represent a valence electron around each of the elements. So for example, for lithium, it has 1 valence electron, so we'd represent it as a dot. For carbon, it has 4, we'd represent it with 4 dots, and we typically will unpair them before we start pairing them. And when you form a compound, atoms will tend to gain or lose electrons if they're specifically ionic, or they'll share electrons if they are covalent. And normally we want to satisfy the octet rule, but we'll talk about some examples where this normally does not happen. And so the goal of the Lewis dot structure is to have an atom that has a noble gas configuration. In other words, it has 8 electrons total, and these can be either taken/shared. But in the case of something like lithium, or even boron or hydrogen, these only want 2 electrons since they want to attain the configuration of helium. Anytime you have a pair of electrons, as you see here, you can typically denote it as a line. And any unpaired electrons will just leave as pairs above the atom, and we'll typically call those a lone pair of electrons. You should expect to see a lot of these on the AP exam. They sprinkle these around throughout the entirety of the exam. And there's generally a certain set of steps that you want to follow whenever you want to draw a valid Lewis structure. One is to find the total number of valence electrons in the atom. Step 2 is to draw what we call a skeleton structure, where you have 1 bond between the atoms as a starting point. And generally, we put the atom, which needs the most bonds, in the center. Oftentimes, this is also the least electronegative in the center of our structure. There are some more caveats to this. Typically, halides, or that would be group 17, and hydrogen are always, or typically at the ends and not the center. So for these, you should generally always put them outside and not in the middle. The second caveat is that third period and lower can have more than 8 electrons. And that's because of their d orbitals. They can do some weird expanding with those, and so we can have more than 8 electrons. And these are always, or typically, will be in the center as well if you have a larger molecule, and I'll show an example of that later. The third step is to place leftover electrons as lone pairs. And then you start with the most electronegative. And lastly, we add double or triple bonds to get to 8, if needed. And we'll do some examples of that right now. So for the first example, we'll look at PCl3. Step 1 is to sum up all the valence electrons in the atoms, taking account for overall charge. So if you have an anion, you have to add an electron. If you have a cation, you have to take 1 electron away. That's the definition of positive or negatively charged. Phosphorus has 5, and since we have 3 CLs, Cl has 7. Since we have 3 of them, we have to do 3 times 7. So we have 26 total bonding electrons in PCl3. We generally want to put the one that makes the most bonds in the center. That is phosphorus, right? Because that has its dot structure would look like this. 1, 2, 3, 4, 5. It can make 3 bonds, whereas Cl can only make 1. So we'll put P in the center, and then we'll give it 3 bonds to Cl. Each of these bonds is 2 electrons, and so we just subtract from our total, 26. We have 3 bonds, which would be minus 6 electrons. And we would end up with 20 remaining electrons. We will then fill remaining electrons around the most electronegative atoms, which in this case is Cl, and so I'm going to just fill in the electrons in Cl. Each one of them gets 6, and so since we have 3 of them, we have to do 20 minus 3 times 6. Where at the end we end up getting 2 electrons left over because it's 20 minus 18. And then we just put the remaining electrons onto phosphorus, right? Phosphorus only has 2, 4, 6. Through the bonds, it only has 6 valence electrons. And so, therefore, we have to put an extra 2 as a lone pair on top of phosphorus. And then this is our valid Lewis structure, and we have 0 electrons left over at the end. Now, if we take this example here of HCN, you can see that H is satisfied. It's got 2 electrons coming from this bond. C is not satisfied. It only has 4 electrons in this structure here, and N has a total of 8 electrons. And so whenever you don't have enough electrons in your central atom, that's when you want to try multiple bonds. And what happens is these lone pairs will come in and they'll form a new bond. And so in reality, for HCN, this is the valid Lewis structure, where H has 1 bond, C has 4 bonds going to it, one in triple bond to N and the other one in a single bond to H. And then N has that same triple bond, but now its last 2 electrons are a lone pair. I also mentioned before that if you have like period 3 elements, they can have larger octets. And so we'll take SF6, for example. Right, you see this and you automatically think like, well, S is on the group 16, and so generally it has 6 valence electrons. If I draw S, it's going to look something like this. And so what this wants to do is make 2 bonds because it has 2 available lone pairs. In reality, phosphorus and sulfur and anything lower can expand its octet because of the d orbitals. And so you follow the same rules, it's just we add another caveat to it of the S can make more than 4 bonds. So the first thing we should do is count all of our valence electrons. We have S, which is giving us 6 valence electrons. And we have F, we have 6 of them, so we do 6. Each fluorine is giving 7 electrons because it's a group 17 element. That will give us 42, and so in total we have 48 electrons to give around. We then pick our central atom. S can make more bonds, so we'll put that in the center. And then we'll draw our skeleton to each of the fluorines, knowing that because it's a 3rd period element, it can make more than 4 bonds if it needs to. From these bonds, we have 6 of them, and each has 2 electrons, and so we subtract 12 electrons from that 48. We end up with 36 electrons left over. And then all we have to do is distribute them on the most electronegative elements. We'll start with fluorine. It needs 6 electrons to complete its octet. We'll do that for every single fluorine. And you'll see on each one we put 6 electrons. We have 6 fluorines, and so we do minus 6 times 6 electrons. That'll get us with 0 electrons at the end. And so despite the fact that sulfur is making more bonds than it theoretically should, it can expand its octet because it has d orbitals under it. And so what it does essentially takes these electrons and decides to bond them anyway. And so now our fluorines are satisfied. The sulfur is not satisfied with the octet rule, but that's okay because it's a little bit lower. And at the end, we have 0 leftover electrons. And so this is the valid Lewis structure for SF6. That's all for this video. Thanks, guys.